Good. So what I'm going to speak about today is a kind of a mixture of number theory, algebraic geometry, and harmonic analysis. To start with, so I'll switch from one to another, and I'll start with a picture you surely know, which is you have a complex plane, or for me as algebraic geometry, it's rather a complex line, and you have zeros of zeta functions. So these zeros are somewhere most likely on the vertical line 1/2, and so that's the Riemann hypothesis, and there is a generalized Riemann hypothesis that says that not only zeros of zeta of S are on this line, but also if you take the Dedekind zeta function zeta k corresponding to the field to a field of algebraic numbers, then the zeros also lie on that line. Now people who study classical zeta function, they usually ask how many zeros are there in some interval and what happens when the vertical line tends to infinity. And I'm interested also in asymptotics, but in a quite different asymptotics. So for me, it's the field k that varies. And so I have some field k1, then a larger field k2, and so on. So this goes to infinity. And I want to ask a question of the zeros. So how to put the question? To put the question, I do the following. I take the first zeta function and I mark it 0 somewhere. Then I want to, I provide the following measure on the vertical line. So the measure is I sum over all zeros rho. I sum the Kronecker delta function in rho of S. So for me, this is a measure. Maybe I shouldn't even write S. I'll write it like this. So the disadvantage is that the integral of this measure is infinite. So what I do is that I would like to divide it by something. 1 over something. So later on I'll tell you what is that something, and so that at least locally this measure will be a finite mass. And so this, what I'm going to divide it by is the genus of the field. So rho here is such that zeta k of rho equals 0. And here I'll write the genus of the field k. And the genus of the field k, I'll define it as a logarithm of the square root of the absolute value of the discriminant of this field. And I call it the genus because on the geometric side of the blackboard, it will correspond to the genus of the curve. Now, I tend this thing to infinity, and I take the limit over ki, so I put I everywhere, of this measure. And something which doesn't look obvious, but which is not very difficult to prove, is that this limit measure exists. And so that's something about arithmetic. And now, of course, we have the counterpart of it for function field. So in the function field case, we have zeta, well, let me write as it is written here. So we have a curve x over a finite field fq, and what is important that q will be fixed once and forever. And now I have zeta function of it, which is defined as a capital zeta function of q to the power minus s. And this capital zeta function, we know for its definition, I'll take the product of 1 minus, so q to the minus s, I'll call t. So 1 minus t to the d to the power minus bd, where bd is the number of places of order d. For an algebraic geometry, you should look at it like this, that you take this curve over fq, you consider it over the algebraic closure fq bar, the Galois action acts on it, so if a point is fixed, it's a point of order 1. If you have 3 points that are interchanged, it's 1 point of order 3, and so on and so forth. We know that it is a rational function with a polynomial px of t that corresponds to the first cohomology of the curve, divided by 1 minus t, 1 minus qt, which is the zero cohomologies and the second cohomologies. This polynomial px is the product of 1 minus omega I t from 1 to 2g, and these omega i's are called Frobenius roots, and we know that they are pairwise conjugate. See, I can write it like this, g plus I bar, and the Riemann hypothesis, which is proved in this case, tells us that the absolute value is square root of q, which corresponds to the fact that if you go to the S-plane, that's, all the zeros are exactly on the line 1/2. So that's what we knew. And now we have several possibilities where to work. So in some cases, especially in the number field case, we have no other choice than to work on this complex plane. But in the function field case, it's more natural to put the zeros, the omega i's, to put them pairwise conjugately on the circle of radius square root of q, and to work either on this line, or, which in my case is more comfortable, I'll work on the segment from minus 2 square root of q to 2 square roots of q, so I take I take a pair of conjugates, I sum them up, and then they fall onto on this segment. And if I want, I can always lift it back to the circle. So here, the point here is omega I plus omega I bar. I do exactly the same. That is, I take the limit, this limit may exist, may not exist. It depends, again, so instead of just one curve x, I consider x1, x2, and so on. What I know is that if it is a tower, then the limit exists. And it exists in some other cases. But so whenever the limit exists, I see that the sequence of fields here, again, I do not need that this is a tower. It's comfortable, it's good when it is a tower, but it's not the only case. If the limit exists, we say that the sequence is asymptotically exact. Now, that's all with the curves and number fields for the moment. Let me lift it. And now I'll pass to abelian varieties over finite fields. So if I have a curve, then there is an abelian variety that corresponds to it, a polarized abelian variety which is called its Jacobian, Jx. What I know about this correspondence is that the first cohomology of x, I do not write the coefficients, but I mean analytic cohomology. The first cohomology of x coincides with the first cohomology of Jx. And also, if I take an arbitrary abelian variety A, then I know that H M of A is just the exterior power, the wedge M of the first cohomology of A. For abelian variety, that shows us that it's enough to know the first cohomology to know everything. For Jacobians, we see that to consider curves and to consider Jacobians is more or less the same thing. And so, now, and instead of, it's many times that I spoke in this room about curves and number fields, and this time I'll speak of abelian varieties. But to make the passage smooth, I'll start from Jacobians. And so, what do we know about these measures? Yes, and maybe it's worth mentioning that I want, in fact, to know this limit measure and to know the limit behavior of the zeta function is one and the same thing. So Serge Vladus and myself defined at some point defined the infinite zeta function of a family, and that infinite zeta function, if you know it, you know the measure. If you know the measure of zeros, you know these functions, and vice versa. So it's all the same. Now, there is a great difference between the case of Jacobians and the case of abelian varieties. And it's about that difference that I'm going to speak today. So how can you distinguish? Well, suppose that you have an abelian variety. Then you can imagine that it is a Jacobian of some curve. If it is a Jacobian, and you can write out not only the zeta function of A, but you can write out the zeta function of that non-existing curve. Because to do it, you need only px of t, and px of t is defined from the first cohomology, and the first cohomology, you know, you just take h1 of A, supposing that A is jx. Yes, so how to distinguish? The main point is that if you really have a curve, then the number of points on it is non-negative. And so for any degree d, we know that BD of x is non-negative. So, for abelian variety, you can formally define BDs by the same formulas as for the curve, passing from the Jacobian to the curve back. But these BDs are no more necessarily positive. And how that influences the measure. So for curves and their Jacobians, the limit measure, let me call it mu of the family xi's. And I suppose that it exists. For you, I suggest that you think about the family of curves and abelian varieties as about a tower. So you have that maps, that arrows that we see above, and then the measure exists and you have no problem at all. And for abelian variety, it's the same thing, that is that, let me write it like this, that A1 is just a subvariety of A2, and so on. Then it's a tower, and the measure exists. And this measure has not only exists, but it has a continuous density. And this density can be, in most cases, so you have your interval, your segment, then from -2 square root of q to 2 square root of q. And over this segment, let this be 1 and this be 2. And you have some graph of that measure. So it can be constant. It can look like this. It can look like this. But what we know is that at this point, at 2 square root of q, there is always the minimum of this density. Maybe not the only one, as we see here. That's surprising, at least when I discovered it and we started to discuss it with Serge. I was very much surprised, maybe you as well, that all of a sudden a measure that you get from delta functions becomes something smooth with continuous density. The main formal ingredient you need to prove it is that the number of points of any degree is non-negative. Now, what do we have for abelian varieties? That's quite different. For yes, before I pass to abelian varieties, there is an open question. for curves. That is, suppose I have such a measure. Is it realizable? Is there a family of curves that has exactly that limit measure or not? We do not have the answer to that question. What we know is that so the question is realizability for the families of Jacobians or of curves, which is the same. And what we know, and that's our result again with Serge, is that the answer is yes, but not for the Jacobians, for products of Jacobians. So you have finite products of Jacobians, and on a finite product of Jacobian, any such measure is realizable, but provided that Q is a square, is an even power of a prime. For odd power of a prime, we do not know even that. And now for abelian varieties. For abelian varieties, we have the Honda-Tate theorem. So the Honda-Tate theorem says that suppose you have a set of 2G inverse Frobenius roots of omega i's. So for any set of omega i's that satisfies all necessary conditions. So they are on the circle and they are pairwise complex conjugate. So for such a set, there exists an abelian variety A. And in my youth, I erroneously thought that this A has exactly these omega i's. In fact, it's not true. What is true that there exists an A such that it has these omega i's with some multiplicity. So say you want to get an elliptic curve. In most cases, you get an elliptic curve, but in some cases, you get a two-dimensional abelian variety with repeated Frobenius roots. But for the asymptotics, it doesn't matter at all. And so now we pass again to number theory. And this is another part of number theory. Has nothing to do with zeta functions. So I'll put an elementary question in number theory. The question is, suppose you have some segment on the real line. And I say that an algebraic number alpha is totally lies in this interval I, so this is I, if all its conjugates are there. So I don't only need the algebraic number to be here, but I need all its conjugates in the sense of the Galois action, all the other roots of the polynomial to lie on this interval as well. And of course, I can ask the same question for any domain on C. So if I have some domain on C, I also can ask, how many are there totally lying inside algebraic integers. And the question is, so you have some set on the real line. From now on, I'll speak only about the real line. Is it true or not that you have infinitely many algebraic integers that are totally there? This question was treated from 1930s to 1960s by Serge, Fekesh, and Robinson. So the last of them was Robinson, and so the results I'll quote will be those of Robinson. And the answer is, let's start with a segment. The answer is that if a segment is small, no. There is only a finite number of totally lying there algebraic integers. If the segment is large, then the answer is yes. And the difference is that if it is smaller than 4, so the length is greater than 4, then infinite number, and smaller than 4, finite. I'll explain you why. So the reason is that take a unit circle. A unit circle has roots of unity of different degrees. And the number of roots of unity on it is infinite. So if you take the segment minus 2, 2, and you sum up complex conjugates, you get infinitely many algebraic integers here, totally lying in the segment. Why the opposite is true? So suppose that you take something which is smaller. For simplicity, I think that let it be centered at 0. So you take something which is smaller, then you can lift these integers. Each integer you lift into a complex conjugate pair on the same circle of radius 1. And you see that these parts should be free. They all should lie in between of two vertical lines. And of course, if you have a root of unity of a rather high degree, then they are dense enough to fall into these two parts as well. And so for small segments, there is only a finite number of such integers. And for large segments, it's infinite. Now, this was generalized by Robinson to the following fact that, so that's Robinson. I'll give you the definitions in a minute. So now I'll state the result. That it depends on the capacity of the set. So now my set, let me call it S, is no more, it's a compact, but it's no more an interval. So for any set on the real line, the question whether there are infinitely many or finitely many totally contained algebraic integers depends on the capacity. So if the capacity is greater than 1, then infinite. If it is smaller than 1, then finite. now I have to do something to put, oops, sorry, I don't mean that, I mean this. Yes, so now let me give some definitions. So one definition was given by Jean-Pierre Serre, and so how can we consider, so we have some compact K, generally in C, but in my case in R, and we're interested in how many there are totally contained integers, and also in what way, in a sense, they are contained there. So we have we have either a finite number of such algebraic integers or an infinite one. If it's infinite, it's countable. Since it's countable, I order them, and I say that let M1, which is M1 of K, in fact, be the set of all such algebraic integers, of all measures that correspond to such algebraic integers. Again, I put a delta function at each integer, and I divide by the length of the orbit, so that this will be measures of mass 1, probability measures, on my compact K, and so these are these probability measures. Now, I threw out the first one, and I get M2. I threw out one more, I get M3. And so on. And I say that M infinity is the intersection of all these Mn's. So, now, if you have some measure that corresponds to some polynomial, of course it's an atomic measure. So, so all the measures here are atomic. On the contrary, and if there is a finite number of such algebraic integers, then somewhere I have no measures more, because I have no integers more. And if it is infinite, then this M infinity is non-empty, and it's not difficult to prove that all the measures here are diffused. Diffused meaning that they are atom-free. So, I knew by results of Robinson that I should consider the case of capacity at least 1, because otherwise it's finite. And then I'm interested in this M infinity. Why only in M infinity? Because all the rest I knew. For atomic measures, I knew the answer, that an atomic measure exists if and only if it is invariant under the Galois action. Because, yeah, sure.
Can we ask what is atomic measure?
Atomic measure is such a measure that a measure of a point is greater than 0. And diffuse if a measure of any point is exactly 0. What I'm going is wrong. It's true for diffuse. For an atomic measure is if it is supported in a discrete set of points, then it's atomic. But because, of course, you can add an atomic to a diffuse, then you get something in between. But when I have a finite number of points for a given polynomial, then it's always atomic. diffuse is rather what I have drawn there for curves. Now, so that's about measures. Now, some analysis. Because you should know what capacity is and several other things. So, for a measure mu, I write integral I of mu, which is the double integral of log x minus y, mu of x, mu of y. And now, for a compact K, I'll define V of K as the supremum over all measures supported in K of this I of mu, of this integral. And I call this the log capacity. And the capacity I mentioned here is just capacity of K is e to the power log capacity of A. So I can return it back. I'll work in terms of log capacity, and therefore, instead of capacity greater than 1, I should write V of S greater than 0. And now what we know is that this supremum is realizable in the sense that there exists a unique measure mu k that corresponds to k, such that I of mu k equals this supremum. And this measure mu k is called the equilibrium measure of K. So this is which one? This one. So this equilibrium measure, for you to get an impression, on a circle, it's just a uniform measure on the circle. On the segment, it's not, and you can easily write it out, passing from the circle to the measure. That's the Tate measure, dx divided by square root of 4 minus x squared. So that's on a segment. If you wish to write it out on a union of two segments, it's somewhat more difficult, but also possible. So on a finite, there is a formula, a complicated one. I'm not going to write it out, for any union of a finite union of segments. So that's the capacity. Now, what I told you already can be formulated as if mu is in mu infinity, then V of the supremum, of the support of mu is non-negative. Yes, and this V can vary, can also be minus infinity. So it's either real or minus infinity. Then it is finite, and moreover, that if we have the support, if v of k equals 0, then well, it's bad to write it like this. I'll write it differently. So if v of the support of mu is 0, then mu equals mu k. Then mu is the equilibrium measure, of its support. Therefore, so this is the necessary condition. So what I'm interested in, I return to the same question as I was discussing for curves. The question is, which measures are measures corresponding to algebraic integers? And which is the same, which measures are measures corresponding to algebraic varieties over of Q, provided that the interval on which you work is from -2 square roots of Q to 2 square root of Q. But of course, the number theory question is more general, because you do not necessarily need to take the interval from -2 square root of Q to 2 square root of Q. So which measures are realizable? So we have a necessary condition, and we have some examples. So inside your interval, you take some set, a compact set, you take its equilibrium measure, and you know that equilibrium measure does correspond to algebraic integers totally contained in its support. Now I need one thing more from analysis. Well, let it be here, for example. I need the notion of potential. So potential is you have a measure, a mass1 measure, and to it we associate a function which we call the potential of this measure. It's a function of one complex variable. It goes, so p mu from C to R and minus infinity, maybe. And this function is defined as the integral over the whole plane log Cw minus z mu of W. So if you integrate it once again over z, then you'll get the logarithmic capacity. So this is the potential, and what we know from harmonic analysis. We know that it is subharmonic, and it's harmonic outside of the support of mu. So on mu it is somewhat small, and then outside it grows to infinity. It grows, roughly speaking, as logarithm of the absolute value, and there it's harmonic. Harmonic in the sense that if you want to know the value at a point, it's enough to draw a circle around and integrate over a circle. So the mean value is in the middle. Moreover, so in K, let K be the support of mu. So inside K, mu, or the potential of mu is constant. I'm wrong. Now I take K and yes, the other way around. So let me take K and let me consider the uniform measure. Not the unimum, the equilibrium measure, mu K. For the equilibrium measure, the potential of mu K is constant, equals V of K inside K, and is harmonic outside. Good. And so that is the state of the art for the Serge talk at the Bourbaki seminar in 2018. That is already 4 years ago. And that's an extremely beautiful piece of mathematical work, and I highly advise those who are interested to start with reading Serge's Bourbaki seminar talk. But after I saw this, I asked myself a question. So, can we get a complete answer? What is the so we know that these equilibrium measures are realizable. We also know that the set M infinity is convex and closed, that in the topological sense of the word. So the question is, so you take many equilibrium measures and you consider all their limits. So what a set of measures do you get? Because I know that if two measures are realized, if a sequence of measures is realizable, the limit of these measures is as well realizable as well. That's easy to see. And that was a question in harmonic analysis, and I'm not very good in harmonic analysis. So I asked Nikolai Nadirashvili, who is here, to help me. The result we get is somewhat stronger than what I hoped it to be. So, no, again, I want to interchange all this. No, you can't press two buttons at the same time. And yes, so the criterion. Well, maybe you do not see it well, I think. So the criterion, that's Nikolai Nedirashvili and myself is the following, that a positive measure of mass 1, of total mass 1, I'll formulate on the interval, which is interesting for algebraic geometry, but in fact you can take some other interval as well, minus 2 roots of square q to square roots of q. But in fact, this is not necessary. Is a limit measure for algebraic numbers in the sense I spoke about. Algebraic numbers, or which is the same abelian varieties over fq. If and only if the potential of this measure is everywhere positive. So, in other words, we proved that the Serre's condition, which is somewhere there in the middle, that the Serre's condition is, in fact, a criterion. So, and so for abelian variety, this answers completely the question I asked. So we know for abelian varieties and more generally for totally real algebraic numbers totally lying somewhere, we know which measures correspond to those sets. And that describes M infinity. And to describe all the measures, you should add atomic measures that are easy to describe. So that's it. So that was again a surprise to me. And now I have several minutes. Maybe I spent part of those to give you the idea of the proof. I think that Nicholas would have done it much better than I do, but still, no, again, the wrong one. Yeah, so the idea of the proof is to approximate any measure with non-negative potential by equilibrium measures. And to do that, we should better understand which measures are what are the equilibrium measures like. So, and I'll draw a picture for you for a potential of mu of z in the case when mu is atomic. So when mu is atomic, then at the place it has some atoms at several places. Its support is discrete, and inside its support it's minus infinity. So the potential goes like this. Now, what you do is that around each such point, you take a small interval. And on this interval, you try to correct it. That is, instead of minus infinity, you just put a kind of constant somewhere here. And now, when you go to the limit, you have more and more small intervals, and you do it in such a way that the Lebesgue measure of these intervals, of the union of these intervals, goes to 0. But the capacity stays positive. The log capacity stays positive, and that's possible. Then you take an arbitrary measure with positive potential. So you take an arbitrary measure with positive potential. You approximate it by some measures mu I that are atomic, and also with that you can do always. But of course, the potential here is not positive because of these minus infinities. And then you approximate each of these measures by mu ij that are already with positive potential, and with the mass going to 0. With the support, which is a union of many very small intervals. Yes, and so then goes the technical details, and the technical details are such that I will be extremely grateful to someone who takes care to check the proof, because I asked 2 people to do it, or I asked many people to do it, but I know 2 people who read this paper. It's Serge Vladots and Jean-Pierre Serre, and they both did a lot to ameliorate what we have written, but none of them was able to check all the details of the proof. Serre wrote to me that to check the details of the proof, I have first to learn harmonic analysis. And knowing Serre, I think that he will do that, but it will take some time. Yes, and the last thing is that we answered, we disproved a conjecture Serre made in those Bourbaki talk. So which one is this? No. So Serre asked the following question. It was not formulated as a conjecture, but rather as a question. So he says, he asked, is the Lebesgue measure realizable or not? Measure on a segment. And so Serre writes that most likely it's not. In fact, it is, provided A is greater than E, which is 2.7 and so on, then the answer is yes. And since 2 square root of 2, not to speak about other prime powers, is greater than E, for the algebraic geometry question for abelian varieties, the answer is yes, always. The Lebesgue measure is also realizable, though it's very far from being equilibrium. So I think I'll stop here.
Thank you. Yes, I was wondering, in your main theorem, can you remove the condition on positivity and consider signed measures?
No, because when you put the question about abelian varieties or about algebraic integers, you have no positivity condition. You mean positivity of what? Of the number of points, or?
Well, I mean, you consider positive measure of mass 1.
Yes, I say positive measure, meaning the following thing, that we take the space of distributions and we say that a measure is an element of those space which is non-negative. Mm-hmm. So that was the meaning. And you mean that if you take an arbitrary distribution? At least
what is called signed measure, meaning the difference maybe of two positive measures?
That's a good question. Cole, maybe you can answer. What do you think? Дай микрофон, Сереж. Everybody's interested, so. You just want to say that you don't know.
It's not. Well, some other questions?
No.
I have some questions. It's rather speculative, I should say. Is there any hope to say something about curves? In any terms, say some conditions, additional conditions on the potential, or which maybe not a criterion, but some necessary or sufficient conditions, something. Personally, I think that it is not possible. But maybe you say you can hope. I don't know.
Yes, as mathematicians usually do, I'm not going to answer your question, but another question that resembles it. So let me reformulate. When you see all this, you have a natural question. So Jacobians are abelian varieties. So these criterion we have for abelian varieties, does it give some restrictions other than those in our paper with Serge on measures from curves? And the answer is no. So if you take those measures with continuous densities that are in the middle, then the potential is also positive and always positive, and that gives these new results about abelian varieties do give any new information about the curves. What you can say about potential of measures corresponding to curves, I just don't
maybe
know.
Not curves, but formally, if BD are positive, can you rewrite this in terms of potential? Maybe not,
Yeah.
but
I can't, but it does mean that you can't.
So one should try. So if there are no other questions, let us thank the speaker again. And